Okay, so we're going to talk about k-means, and this is going to be an example, the first example of an unsupervised learning algorithm in this course. Okay, so in this explainer, we're going to go through the principal idea of k-means, understand why it's an unsupervised learning algorithm, and particularly a clustering algorithm. And then we're going to go through the basics of how the algorithm can be trained. Not too much detail, but just the basics so you know that what programs like sklearn are doing under the hood. And then one of the key questions is, how do we pick the number of clusters k? That won't make sense at the moment, but we'll go through that. So first, let's just remind ourselves what a unsupervised learning algorithm is. So in unsupervised learning, or let's start with supervised learning. With supervised learning, what you have is you have labeled examples. So you have inputs x, and then you have some process which you're seeking to learn, and that gives you target out y. In unsupervised learning, we don't have these labels y. We just have a set of data, input data x, and what we're really trying to do is discover patterns in that data set, which allows us to do various other things. So let's just get rid of this. Okay, so in unsupervised learning, so it's an unsupervised learning algorithm. And so we have a data set x. And so this little squiggly notation, remember, is just nothing more than set notation, and just means a bucket full of samples. So we have n samples. And so in unsupervised learning, we're trying to find patterns in this set x. So just a quick recap, there are two types of unsupervised learning that we're going to go through. So the first one, which I won't go through quickly because this k-means isn't one, is dimension reduction. And so each of these little elements in here, let's grab one of these. So xn and all the others live in Rd. Now what does this mean? This means that the input can be represented by a vector, a list of numbers essentially, all the way down to xd. So there are d numbers that represent this. So in a typical input, which could be pixels, for example, in a picture, then this would be the value of the color in each of the pixels, for example. Could be anything. So if it was a stock market model for something, it could be inflation rates, the FTSE 100 price, etc. So these are just the values which describe that sample. In dimension reduction, our aim is to try and reduce the size of this representation. So we want to find some. So we want to find some x hat. So it's just an approximation which it lives in Rm, and m is much smaller. So we write two less than signs, much smaller than d. So the idea here is that we can we discover patterns in this dataset x, which means that we can actually represent it in a much neater, lower dimensional way. So that's one type of unsupervised learning algorithm, which k-means isn't, so we're not going to spend too much time. The other is clustering, right? So k-means is a clustering algorithm, and clustering algorithm kind of does what it says. What you're trying to do or seek are natural groupings in the data set that allow to take your data set x and place them into subsets or clusters. You can then do various things with those subset or clusters. They're really nice applications in terms of image segmentation, compression, and we'll try and go through a few of those. But the principal idea is to find natural groupings for the data set x. Okay, so let's get on to k-means. And so just a bit of set notation here. We're going to be looking at our whole set x, but what we want to do is we want to partition, separate, into subsets. So we write this as x1 union x2 union x3, all the way up to union xk. So this is where the k comes in, right? K stands for the number of clusters. So k is the number of clusters. And so if you don't know set notation, it's not complicated. So if I've got one set A and I've got unioned with another set B, I can draw a little diagram. So basically, the union of two sets is everything. So you basically, it's all the elements that are included in both A and B. Right? So all this says here is that X, our data set X, is now made up of K smaller buckets, which contain the elements. And now, kind of, not only union, in set theory you have A intersect B, and when we're looking at this, what we're really interested in is this overlap, and this is called the intersect, right? So the important thing about the sets that we have to make up the clusters is that each of them don't intersect. So we can write this as x1 union x2 equals the empty set. So what this means graphically, you could imagine x1's this set, so this is x1, this is x2, and the intersect, the overlap of the two, is empty. Doesn't contain any elements, right? No common element. And so x1 and x2 don't overlap, x1 and x3 don't overlap, actually any pair don't overlap. So what we write, if I get rid of these indices, we write I, j, for I not equal to j. It's a bit of maths notation, but all this means that if I and j are different, so 1, 2, 1, 3, k3, etc., then this must be empty. So none of them overlap. Obviously if they're the same, they obviously do perfectly overlap. So this is why for I not equal to j. So quite simple, but basically what this means, we can draw what this means graphically. We can say that, let's draw a picture. If this is feature 1, my problem, feature 2. So feature, I just mean input of component of x. And then let's say we've got, let's make them obvious clusters. So what we're trying to do here is if we make this one set, K1, is different color, K2, red, K3. So just to labour the point, all the points are part of X, so all these black dots are part of the set X, but we've partitioned or clustered elements into 3 subgroups, x1, x2, x3. So in this case, K would be 3, because there are 3 clusters, and none of these sets overlap. And so that means that any element in one of these sets only belongs to one of the clusters, right? So need a bit of notation. Problem with maths is it requires notation. So we're going to introduce what we call a flag, which indicates if a point, a data point in the data set lives in a particular cluster. So we're going to introduce a flag. I call it a flag because it sort of indicates whether it's in or out. We're going to call it RIK. Right, and so let's just write down what this is. So RIK is basically a number, and it's either 0 or 1. It's 1 if xi, so the ith sample in the dataset X, lives in partition K. And it's 0 otherwise. So probably easier to see what this means graphically. So let's go through a little example. So this flag RIK can be seen as a matrix. It has two indices, or matrix or table if you're not familiar with matrices. And so let's draw this out. Okay, so if we have the cluster at the top in the columns, okay, and so this will be cluster 1, 2, and 3. And then we have the sample. So typically there'd be loads more samples than this, but I can't write them all out. And 1, 2, 3, 4, 5, 6. Okay, so then in each of these, let's pick a different colour. So in each of these rows, this row, the first row indicates is the information about the belonging of sample 1. So if we say, okay, 0, 0, 1, what this means is the sample lives in the first sample lives in the third cluster. So let's just randomly fill out these. It's not a real example, it's just to show you. Let's look at this one, for example. So in this case, we have R, the third sample, so first index is 3, third cluster equals 1, but R32 equals R31 equals 0. So the third sample lives in the third cluster. Now what you notice is there's only one 1 per row, and this is exactly the thing that a sample can only belong to one cluster. You couldn't have this, for example, right? Because that would mean 3 would live in 1 and 3 as well. Okay. So another interesting thing is if we wanted to know the number of samples in the third cluster, we could just add up this column, so the third column. And so in this case, in this example, so let's look at cluster 3, we could have, we know it's 1, 2, 3, so n is 3. And so n3, the number in cluster 3 equals 3. We do that by summing up the column. And so if we're going to write some mass notation, we would sum up over all samples, so from i's 1 to 6, so down all of the rows, and then we have ri3 in this case. So here's a bit of a formula. Nk is equal to the sum from i's 1 to n samples RIK. So nothing profound here, but just a generalization of what I said. So in this example, I've got 6, but that's just general. If I could have n samples, I would just sum up over all n, and then I can replace the third, because I was looking at examples specifically for the third cluster, I can change that for k. Okay, so now we talked about k. So what does the mean, where does the means come from? So interesting thing that we can do, and let me just grab this. So now within a cluster, we can ask the question, what's the average sample in that cluster? And so in the middle of here, we might have, if we averaged all of those in this cluster x2, then we could say, well, actually, there's sort of an average sample, a mean sample, and that's where the mean in k-means comes from, and we'll call that mu2 in this example. But in general, we can build a mean for each of the clusters. And so the way we do that, let me write down, we write mu k. So for any cluster k, we sum over all the rows, so sum over all the samples, n, and then we write our flag RIK X I divided by the sum for I equals 1 to n RIK. So what you'll notice is this bottom bit is just nk, so the number of samples in the K cluster. And then this one just takes, so if the sample belongs to this cluster, RIK will be 1, and then we're just going to add up all the vectors together and then divide by the total number that belong in that set. So this is just a simple average vector that belongs to that cluster. And so the concept behind k-means is that we want to say that the best cluster, or the best clustering, minimizes, reduces as much as possible the distance of the samples in that cluster from its mean. So let's write that down. So k-means, the key concept is find the clustering, which actually means find the values in RIK, which reduces the distance of samples in the cluster to the mean. So in machine learning, or optimization maths generally, find a clustering which minimizes, reduces, means that we're going to have to write an objective function. An objective function just means something that we're seeking to achieve or reduce, something that allows us to evaluate for a particular assignment of clusters, how good is it relative to another choice, and then we try and use this in the training process. So we define an objective function, and for k-means it's actually called the inertia. And so don't worry too much about the notation when I write it down. We'll talk about it. It might look complicated. So we write J for an objective. So we're going to sum over all of the samples, and then going to sum over all of the clusters. Big K. Here's my indicate, my sort of flag, whether it belongs or not. And then I'm going to write the distance between the sample X and the mean of its cluster. So it's the squared distance. So what this is doing is quite simply, if it belongs, so this just says, does it belong in this cluster? And if it belongs in this cluster, then I'm going to calculate the distance squared between the sample that belongs in that cluster and the mean. And so I want to try and choose the these values so that reduces the total distance. Right? Okay, so let's get on to training a k-means model. And so for this bit, hopefully it's of interest. If you're just looking to sklearn, this is what goes on under the hood. Often a slightly more sophisticated, streamlined version of this. I always think it's useful to know what's happening in training, because if training doesn't work, it sort of indicates what parameters you might play with to improve training. So I think it's worth understanding, but you won't actually need to do or write code for this, even though I do sort of set it as a little challenge. See if you can write a bit of code that does this for a simple example. So as we discussed, really, the things that you can play around with are the assignment. So k-means is really about finding RIK. And so we'll just go through the algorithm here. So first of all, and one of the assumptions you must first do, and we'll talk about how you pick it in a minute, the first thing you must do is we set the number of clusters. And then, to start the algorithm, so this is kind of point, let's give it a number, there you go. And then 2, we randomly assign samples to clusters. So this basically means we set RIK values. So we do it randomly to start with. Then we proceed by doing a loop, right? And then we basically, so we're gonna do a loop until J, the objective or inertia, doesn't improve. Okay, so in this loop, what the first step we're going to do, so let's call it 3A, to say that you're going to repeat this. We first calculate the mean for each cluster. So we calculate mu k, right? The next step is we loop through each data point, each data point, and then we calculate the distance. We calculate the distance which is between the sample, so xk, and the mean of a cluster. So this actually requires you calculating, so this is n times by k distances. Okay, and then, so it's quite expensive, particularly for big data sets. We then assign, or reassign sample xi to the cluster k with minimum distance. And then the final step is we recalculate the j, right? So what happens here, so what we mean by loop is we're now going to just repeat this. So we'd set some threshold on how much we'd sort of expect j to improve. If it doesn't improve, then we stop. But if it looks like it's improving by changing, what we'll do is we'll just go through repeated loops of this step until we get the answer. So I've set a challenge in the notes online, so you can say, can you write a basic implementation of this yourself? Not essential, but if you'd like to try out your Python programming, it's quite a good example to do. Obviously, where do you think the computational cost is? Do you have ideas about how you could speed that up? And then how do you pick k? And that's what I'm going to talk about now. So it's a bit like k and n, if you've looked at that method. There's this sort of parameter k that you kind of have to set at the beginning, and then you're not really sure what you should take it for, obviously, until you start analyzing the problem. Same with k-means. Unless you've got very distinct sets that you can cluster it by and you don't really need an algorithm, then k won't be that obvious. I'm going to talk about two techniques used widely to sort of understand what the optimal, or what a good choice, I wouldn't say optimal, of k is. One is called the elbow method, which is basically just plotting stuff out and then looking at the results. The second one is called a silhouette coefficient, or silhouette validation, and I'll briefly describe what that is. Okay, so let's start with the elbow method. So what you can do is you can actually run k-means multiple times with different numbers of k. And what this would generate, once you've trained your algorithm, you could have the final inertia, so your j, or inertia, once you've trained it. And then you could plot, so there's no point having one cluster. So 2, 3, 4, 5, etc. And what you'd expect to see is, well, you will see a decreasing function. Let's just put, so what you'll see is a function that comes down. The reason it's decreasing is that, obviously, if you pick the number of clusters equal to the number of sample points, the inertia must be 0, and that's because in a set of 1, the mean is itself, and therefore the distance for that sample away from its mean is 0. As you increase the number of clusters, you will get more and more inertia, but it's a strictly decreasing function as you increase the clusters. But typically what you'll see is the inertia comes down. I'll deliberately draw two separate graphs to try and describe why it's the elbow. So most of the improvement in inertia is likely to come up to a finite point in number of clusters. And then beyond that, there's little improvement or very slow improvement in terms of decreasing the inertia. And so the simplest heuristic method for choosing the K and K means is to look for the elbow. And in this example, the elbow is described here. So what we see is we have a very steep decrease in inertia up to 4 clusters, and then after that the gradient's changed, and so we see this as like a bend at the elbow. So this gives a sort of eyeball way of picking a natural choice in K, which sort of compromises you kind of want as large groups as possible because that's kind of neatest going forward in whatever analysis you'll use it for, but you want sufficient accuracy, so it's a compromise between these two elements. Okay, and then the second part, and this is a metric, so it's not just plotting out, but there is a plot that comes with it, which is quite useful, and I'll go through this in the example walkthrough. So silhouette, I can't spell silhouette, validation or coefficient. So I'm not going to go through the maths of how you calculate the coefficient. I'll put that in the notes somewhere. But sklearn actually provides it for you. Signal analysis is basically ends up being the study of the separation distance between two clusters, and it's kind of a measure of how distinct they are. So a silhouette coefficient gets basically a score which ranges between -1 and 1. And so what this means is so if you have a silhouette coef of 1, then this indicates the sample is as far away as possible from the neighbouring clusters. So it's far away from other clusters. So this indicates it's not close in terms of, you're not uncertain, you're very clear that it should be assigned to that cluster. A coefficient of 0 indicates sample is on the decision boundary. So it's very close to a neighbouring cluster and could easily be assigned either way. So negative values actually mean that you should the sample's been assigned to the wrong cluster, so it's actually suboptimal. So if you have a trained module and you then have a coefficient of less than 0, a negative value, it actually indicates that it should be another cluster. Okay, so I did try and draw you a picture of a graphical representation of the silhouette validation. Turns out to be quite a lot harder than I was expecting. So I'm going to leave that to the example that we show you. It's much easier to do it in a matplotlib in Python to show you what plot looks like out. The key thing is that silhouette coefficient is a number for each sample, and it basically, if it's 1, it indicates that it's clearly in that cluster. 0 means it's indecisive and it could be close to being assigned to another cluster. A negative value tells you that it's assigned to the wrong cluster. So concluding marks. So key points to remember. K-means is an unsupervised learning algorithm. It is a clustering algorithm. the principle behind the method is to assign samples to the clusters where the distance to the mean of that cluster is smallest. We have a bit of a challenge about how do we pick the number of clusters. So the simplest way to look at this is called the elbow method, where we basically build lots of models for different numbers of clusters, and then we look to see where we get the best benefit against complexity. So we look for the elbow in the plot, or we can evaluate what's called the silhouette coefficients for each of the samples. We can calculate the average silhouette coefficient, so we want that as close to 1 as possible, or we can just look at the distribution of them and see how uncertain the assignment are to each of the clusters. So next things to do, there are a few challenges in the notes. I encourage you to do them, maybe to write your own k-means algorithm, just to make sure you understand the concepts. There's also some questions around like how you might improve the cost. If you're not interested in doing that and you kind of want to just get on and use it, there will be a walkthrough which goes through some simple examples using sklearn.